Okay, so let's start today's lecture. Okay, so today the topic is the latent variable model. And sorry, first of all, assignment 1 has been uploaded on the Blackboard. So here, contents and the lecture file. Assessment. If you go there, the assessment, you can see the assignment. Okay, so here, as you can see, it's very basic. Okay, not difficult. Okay, so very. Okay, so it is total 6-7 question, but actually very simple. Okay, so the deadline is 3 weeks later, February 25. Okay, so except for the New Year's week, you will have 2 weeks. Okay, for the assignment 1, but actually, I believe it's enough. Time should be enough. It's very simple. Okay, not complex. I mean, this is question 1, question 2, question 3. Actually, is a bachelor level, I believe. Okay, so and how to upload in the online submission. Okay, maybe you know how to do, right? Maybe I guess you already have experience at least once for the TA in other classes. So same, you can submit your solution here. Okay, deadline February 25. Any question for this assignment 1? Okay. Okay, then let's start today. So until the week 1, week 2, week 3, you learned about the regression models and some basics of the statistics. So you learned about the assumption, how to estimate the beta, and how to make a building strategy, and then types of variable, elasticity, and the nonlinear transformation, like a box-Cox transformation. Okay. And then here, before we start, I mean, this is the general data. I mean, when you analyze your topic, you may use your own data like this. Okay, so pen. So they are attribute or variable, depending on your context. And then this is the observations. Okay, observation can be individual or your number of experiments or not, or whatever. Okay, but anyway, for the statistical analysis, our data looks like this. Okay, so here, I mean, how many variable you have, I mean, something blah. Okay, so here, for the data analysis, what is the basic is that regression analysis. But the point here in the regression analysis is that of course, there are some major assumptions, but the most significant assumption is that these attributes should be independent, right? But in reality, in your data, actually, most of cases, once you get your data, these attributes are not independent. They are somewhat related. So normally, once you see the publications in the top journal in your field, so people, even though they try to analyze their data, they normally use some advanced model, advanced statistical model or machine learning algorithms and whatever. Okay. So today, last week you learned about multi-collinearity. It's about the correlation between attributes. Okay, so today lecture is about that. So, okay, my data will be the variables will be correlated. Then what we can do? Okay, so today is about one of the answer for this question. Okay, so today you will learn about the concept of the latent variable. Latent variable means that variables are latent. Latent is like unseen or unrevealed, something like that. I don't know in Chinese what for this one, but anyways, it's something like that. Unseen, unobserved variable. Okay. So first one, I will talk about the structuring data, and then PCA, the principal component analysis, and the factor analysis. Actually, the PCA is quite related to the machine learning clustering. Okay, and the factor analysis and the structural equation modeling. Okay, so first one is about the general structure of your data. Sorry. So as I emphasized several times again, what you will do normally if your PhD thesis is about the data analysis, you first check some your observations and then choose one of them for your topic, whatever, some kind of one variable. And then this will be your topic, why. And then based on this, you try to analyze the relationship between between y and the another x here. So this is the general approach for the data analysis. Okay, but here, so what is the basic assumption here? We normally use the y equal f. This is the bold. So y equal fx. But what is the basic assumption, basic implication here is that we assume that x affects to the y. Right? X significantly affects y. Y is your topic, whatever, in your field. Okay? But of course, we can wonder, isn't it like this? Y influence to the X? It can be possible, of course. But normally when we do some statistical analysis, we directly, we arbitrarily assume that, oh, X influenced Y. But of course, in real data, it can be reversed. So in this case, your analysis can be some problematic, right? And also another case, we assume X affects to the Y, but it can affect X affects to Y, but through the other attribute to Z. Okay, so in this case, this is about the causal relationship, and then this is about the indirect mediate relationship. So X indirectly influence to the Y. Okay, and then some relationship. Yeah, I mean it's the general, and then this is the also very important topic in general. So what it means is that, okay, in reality, X influenced Y. This is the clear. But the point here is that our data, your data, every data is not perfect. What it means, you measure X, but actually it's not exactly X. So it should be X plus. So what is the X prime? Means that X plus epsilon, right? Epsilon means that measurement error. So if your PhD work is based on the experiment, when you measure something in your experiment, of course, it's the matter of the human beings. So it can be some measurement error there. Also similarly, y prime, y plus epsilon. So in this case, you want to analyze the relationship between X and Y, but actually your data including X prime and Y prime. So in this case, I mean, the analysis could be some problematic. So role of the measurement errors in observed relationship there. This is about this relationship. Okay. So in this case, especially the measurement case of the measurement error, many important constructs are not directly observable. Okay, so even though in your experiment you try to measure something, but it can be problematic. So these days, many people we use the big data, but the problem is that the big data, especially there are lots of error, measurement error there, because it's automatically measured. Okay, so some unobservable variable, unrevealed variables are indirectly measured through the observed indicators. It's kind of proxy variable. So for instance, if you are working in the environmental engineering or some energy engineering, maybe the individual's attitude toward the gas taxes may be important issue. Some individuals' environmental consciousness, the warnings, concerns also can be important issue. And then also their perception of the safety or convenience can be a significant problem there. But normally it is difficult to measure directly. Okay. So in this case, the issue is called the endogeneity. Endogeneity means that when explanatory variables is correlated with the error term, it means that, I mean, simply your measured X is not correct. You have data like this. Here, maybe you have a, here, you measured it as a 10. 10 is the variable, the value of the variable. The point is that this value normally is not exactly correct. It has some error there. Okay, but normally many researchers, we ignore this error and then we believe that our data is perfect. And then we analyze the relationship between X and Y. Then of course the result could be biased. Okay. So in this case, when this kind of endogeneity measurement error happened, omitted relevance variable or simultaneously reverse causality. And the measurement error in predictors, I mean, this is what I explained already. And then anyway, in this case, your result, regression estimator become biased. So you run the biased, right? The population. Sorry. So here, population. World. Here, we assume there are some two values. This is the knowledge, perfect knowledge, beta. We call it true value. Actually, this is our point. We want to identify beta. We want to know beta. What is the beta? The global knowledge and the population, the world knowledge there. But of course, we cannot collect all the data for the whole world. We cannot collect the data for the whole population there. So what we do, we just maybe should be. We only check part of the whole world. And then this is our sample. Normally, we call it data. And then we believe our data representative to the whole population, whole the world. And then we analyze this data. This is your work, normally in PhD. And then you get some parameter beta here, estimate the parameter beta here. And then what you argue is that they are simply they are same. But statistically, we do not say it's same. We say unbiased. So this is what you do in your PhD work. If you are PhD work in data analysis. But in this case, like endogeneity issue, it cannot be same. And then your result can be biased. it means that your estimate beta is different for the true value. Then the question, then in this case, what your result can talk about? What is the academic contribution here? Actually, not many things. So if your parameter is biased, then it means that your result is nothing actually. Not academically useful. So here, therefore, it is important to get the unbiased parameter there. So in this class, at least in the first lecture, I repeatedly emphasize that we need to get the unbiased parameter. Why? Because our ultimate goal is the true value, true knowledge. So if your data include like this issue, your regression estimator beta become biased and incorrect. So it's not much useful. Okay. So here, the goals in the observational and explanatory studies. Actually, this is the, I believe, at least in FCE, this is the general students' work in PhD thesis. Okay. So in many real-world studies, this is your PhD work, we face no experimental control. It means the big data, right? We just passively collect the data. And then many times even the Hong Kong government open the data. And then we believe that, oh, this data is good. But we don't know. Many times it's not good, actually. Okay. And the observation data only, it means that not many exit. Okay. And then limited or no strong prior theory and the explanatory failure or study. Okay. So primary objective in early analysis, uncover empirical structure in the data. So before you conduct your final analysis, you first need to understand your data, the structure of your data, okay? To inform the model specification later. So normally, I mean, what is the rule in the data analysis is that we first understand the data structure. Understanding the data structure. And then based on the understanding the data structure, we build model, proper model. And then we analyze. But what is the problem in reality is that we normally skip this process. And then we just use the build model, any new model, some innovative model. And then we just apply the model to our data. And then we present our results. But many times, most of them, it could be okay. But sometimes it can be problematic. Why? Because the model is not matched with your data structure. So this is the main reviewer's point once you submit your paper in the Q1 journal, okay, in terms of the statistical issue. Okay. So here, then to build my model, how I understand the data, my data structure, is that the three topics today. Principal component analysis, PCA. So this is the very simple. So it's widely used explanatory technique. So it's about the clustering. I will show you later, something like that. So clustering is related to the machine learning, very, very, very close. Okay. Machine learning clustering. Maybe Professor Maui will teach about this maybe in the second half. Okay. And the factor analysis, I will also explain later, but it's like this: x1, x2, x3, and then I make it g1. Combining similar correlated attributes together, I will make a new variable. This is about the factor analysis. So here, it means that, so here, I can try, based on my data, I can try to analyze the correlation between variables. And then the result shows that they are correlated, strongly correlated. And then they are strongly correlated. And then they are strongly correlated. Then I can make a new variable like this, Z1, Z2, Z3, something like that. This is the factor analysis. Okay? And then the goal, ultimate goal is that the structural equation modeling. this is the how to say, most comprehensive framework in the data analysis, and then it handles the latent variable, endogeneity, mediation, many statistical issue, and it allows the complex tensor relationship and feedback loop. I mean, I will explain later. Okay, so here this is the summary of the comparison among these three methods. So PCA, what is the advantage? The quick pattern discovery, clustering. And the factor analysis, scale, development, attitude, I mean, new variable, Z. And the structural equation modeling together. Okay, I will explain one by one. And then here, so first issue is about the principal component analysis. Okay, so it's something like this. This is the principal analysis. Okay, so here, based on your data, maybe I can explain. So let's return to the general data format. So let's assume I only have 3 attributes, x1, x2, x3. This is my data, for instance. And then I can try to understand my observations here. This value, some value there, right? Blah, 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 blah. And then especially here, and then I will make it this 3 variable in the 3-dimension graphical representation like this. Variable 1, 2, 3. So in this case, I can plot the observations in the 3-dimension. And then here, based on this PCA technique, I can split them into the 4 clusters. So here, this concept, as I explained many times, machine learning. Maybe, it's quite similar with the machine learning clustering technique. So actually, when people talking about the machine learning clustering there, they start from the general PCA issue. And then they pointed out what is the limitation of the general PCA, and then they proposed the machine learning clustering algorithm there. Okay. So then a question, so how we can divide it? So we normally do to reduce dimensionality, transform a large number of variables into a smaller set of the new variable. Okay. Interpret the structure, discover the meaningful pattern. It's like a clustering. And the dimension in multivariate data. Multivariate is that X, there are many X variable there. Okay. So how we decide it? We normally achieve this analyzing variance covariance structure. Okay. And the core idea is that variance. Variance means that, so here again. So let's only focusing on the X here. In this case, we can see here, this is X1. And then maybe it can be something like this, value in the observation. Many observations, value 1, 2, 3, 4, 5, 10, blah, blah, whatever. And then this is the distribution for these values, right, all together in all observation. Then we can calculate the variance across the observation. So here PCA, we consider the variance of each variable across the observation. Okay. So PCA create a new variable called the principal components. Okay. So each principal component is a weighted linear combination of the original variable. So I will show you in the examples there. And then the first PC captures the largest possible amount of the variance. And then the second PC captures the next larger amount. For instance, here, maybe it can be PC1, and then it can be PC2, it can be PC3, it can be PC4, something like that. Okay, this is the technique of the clustering. Okay. So here, and then goal, a few components. P is the number of parameter, and the K is the number of cluster. So explain most of the total variance. Normally, we do it 80%. Okay. So replace many original variables with fewer meaningful dimensions there. Okay. So ideal situations for the PCA observational data. And then many correlated variables. And then looking for underlying patterns or latent dimensions and then explanatory analysis phase. But the problem here is that PCA is not useful when original variables are mostly uncorrelated. Then we can just use the regression model. And then data come from randomized experience. I will explain you later. And then you already have a strong theoretical model, something blah, blah, blah. Okay. So for the PCA, there are some mathematics, but I mean, just for your idea. So data matrix, let's assume we have n observations and the p variable. So here, n observations and the p variables there. Okay. So therefore, it's a matrix. The data is a kind of matrix there. And then here, first principal components, they conduct the kind of regression model. It's not directly regression model because it's more like a optimization. So maybe I believe all of you will know about the mathematical modeling, right? Optimization, because PhD course, our CE also have an optimization course in mathematics. No. Okay. Okay, so just for the principle here. So what is the purpose is that, so this is the Z1. And then this is our objective. Okay. We want to calculate the Z1 based on A11, X11. This is the variable. And then they are parameters. A is the parameter. The X is a variable. Okay. And then what is the constraint is that they are sum of the square should be equal to 1. Okay. So based on this condition, we want to maximize this one, variance of the Z1. Okay, so some mathematics, blah, blah, blah. So it's about the optimization. So I will not explain more detail about this. Just this is the how your software will calculate it. Okay? And then same way for the Z2. And then this is the constraint. And then we calculate the Z to maximize their variance. Okay? So Z1, Z2 should be independent, non-correlated. So this is the logic. So mathematically, I mean, it's okay. I mean, just this is the how to software calculate it. And then principal component are ordered by variance. PC1, first component, big portion, most big portion. Second one, the next big portion, something like this. Most big portion, second big portion, third big portion, and the first big portion, something like that. This is the how your software will calculate. MATLAB or R or Python, whatever. They calculated based on this for the PCA. Okay. So important property, all principal component here Z1, Z2, Z3, they should be independent each other. Okay? And then here, what is the output of the PCA is that we can have two different values, eigenvalue and eigenvector. Actually, similar meaning. So it's based on eigendistance, something like that. So they can, based on the something complex mathematics, blah, 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 blah. And then PCA, they analyze the variance covariance matrix in the S, your data. And then they provide you the eigenvalues, something like that. So this is an so this is an example. So here, this is the PC1, PC2, PC3, PC4, something blah blah blah. And then the output, SPS, even SPSS is okay. SPSS, Python, MATLAB, R, whatever. This is the important output there. You can see PC1, they have a normal, PC1 has the largest eigenvalue. So PC2 is the second largest. So eigenvalue, some complex relationship, but how you can think a portion, something like a portion. You can understand that eigenvalue is like a portion of the PC in your data. So what it means, you remember here, PC1 explain the most variance, okay, most observations there. It means that they have a largest portion in your observation. So PC1, PC higher, how to say, the portion means that the portion in observation in your data. Normally PC1 has higher than PC2, right? Then eigenvalue for the PC1 should be higher than eigenvalue for the PC2. Why? Because eigenvalue is like a measurement of the portion. Okay. So I didn't include the detailed formulation about the eigenvalue, but you can just understand that if you need to use this PCA, then eigenvalue is like a portion of the data. Okay. So eigenvector is like a coefficient, but we normally more use the eigenvalue than eigenvectors in reality. Okay, and then total variance explained the sum of the all eigenvalues is the total variance in the data. So why we usually use the correlation matrix? Maybe it's later. Maybe I can explain later. So here, for instance, another practical issue is that, so okay, now the software, they generated 8 principal components. Then should we use all of them? Then actually it's no. Then how we decide the number of the principal components in my data is that cut there. 1. 1 is the threshold. So in this figure, it's called the Kaiser criterion. So when we analyze our data, we normally select only the principal components whose eigenvalue is larger than 1. Okay, so this is the practical technique there. Okay, so this is an example here. So this is the case here. So you can see PC1, PC2, PC3, PC4, PC5 is 8 PCs there. Okay, and then for each 8 PC there, they have a different variable. 1, 2, 3, 4, 5, 6, 7, 8. So as you can see in this data, in reality, how they do here, 8 variable, something like that. I mean, I don't know how make it graph, but it can be 8 dimension, right? And then they cluster similar observations, something like that. Okay. So in this case, we can see this is the eigenvalue. So before the eigenvalue, we can see here cumulative. Cumulative is the proportion. Okay. So again, earlier number PC1, PC2, PC3, they have a higher sequence of the portion. So PC1, 44%, right? PC2, higher than 26%, and then PC3, 13%, and then others only 6%, 5%. Even this is the 0.5%, so it's very slow, very low. So in this case, how we decided? Only consider eigenvalue larger than 1. Okay? So 3 components. And then we delete this information for the final analysis. Okay? So let's return there. And then why we usually use the correlation matrix problem, low variance matrix, some blah blah is too mathematics. So I mean, you can skip there. So what is the important thing? Based on the screen plot, and then we choose the principal component whose eigenvalue is larger than 1. So we can see here, cumulative percent. So if we choose them, then it means that these 3 principal components explain the observations around 85% already. So this is consistent with the component here, our goal. So our goal of the paired principal component analysis is that to explain our data between 70 or 90%, but normally we use the 80%. So here we already used the explain the 85% based on 3 principal components. So this analysis can be acceptable. Okay. So interpretation, what do the components mean? So here, PC1, PC2, PC3, what they mean? Principal component loading. Loading means that these parameters. Okay. It means that it tells us which original variable contribute to the strong to each PC, and the direction and the strength of the contribution. So here we can see, maybe I have so here PC1. Let's see the focusing on the PC1. So here what we can see, largest value, this one. We can compare the absolute value of the loading parameter for the PC1. And then we can make a ranking there in that PC1 influenced by age. Age is the largest, and the residence is the second largest, and the employee and the savings, something like that, right? So we can realize that PC1, it is sensitive to the people's age and the people's residential, maybe residence type, maybe, and then its employee status, and then their savings. And then how about the PC2? So note that, so this PC means the Z, right? So here, what we assume, what is the purpose to generate each cluster? So first principle, second principle, maximum variance Z1 and Z2, right? What is the basic assumption is that each paired component should be independent, not correlated. So we can see the result in that normally. So here, the significant factor is normally unoverlapped. So for instance, here, PC2, this one and this one, right? Number 1, 2, here. These factors affects to the PC1 strongly. And then these factors strongly affect to the PC2. And then for this one, PC3. So normally it is clearly distinguished. Why? Because we calculated they are independent. So significant factors, normally they are distinguished. So in this case, we cluster our data with the similar observations together. Okay. So this is about the principal component analysis. Any question so far? So others are okay. Maybe your concern is about the quiz 1, right? We will have a quiz 1 in week 6. So I mean not mathematics. For instance, something like that. How many clusters should you use there? And tell me what is the reason, something like that. And what is the purpose of the PCA, something like that. So it's very basic, right? Some kind of this level. Okay. Quiz, I didn't make the quiz yet, but normally it will take 1.5 hours. But normally it's for the one hour, but I will give you around 1.5 hours. So most of questions will be very not difficult, but I will make a 1 or 2 some a little bit a complex question to distinguish your grade. Okay, but normally it's very easy. And then I know most of you received the fellowship, right? And then what is the criteria for the minimum grading? B0 or B plus? Could you tell me what? B plus.
She said pass.
Pass, only pass is okay. I don't think so. It's B minus. Should be higher than B minus. Okay, I see. Okay. So I will give you, I mean, the grading. I believe the PhD grading is not important, but I mean, in terms of fellowship, it can be significant. So normally, I will try to give you the most good, better grade. Okay. Okay. So I mean, let's take a 10-minute break, and then I will continue the factor analysis. Okay. But note that my part will be this level, but I'm not sure the second part. Okay, maybe the machine learning part can be more mathematically difficult. So I don't know. I mean, it's out of my authority. Okay.
Tip for you. I randomly saw other teacher just directly touch this screen and they can join.
Yes, but in this lecture room, I cannot find the.
Yeah, you can directly touch the screen.
Okay, I see. Okay, okay, I see.
Also use the spin.
Yes. Thank you. -1.
Here, so it's like, for example, there are like 8 software generated, but eventually we just use the first 7 one. So mine.
Because if it is too many, I mean, it depends on your purpose. But if it is too many, maybe you can use it for your further analysis. But because their portion is too small, and then so maybe if you can use it in the regression model, then from this result, the parameters can be biased.
Yeah, but for example, here I just use the first 3 because they are all like larger than 1 for the engine values.
Yes.
But like for example, for the previous slide you mentioned, it's like the -1. Like here, like the 8 minus 1 is like 7 for 7 components. So eventually, like the criteria is about the engine values that is larger than 1. It's not about like the number, is it?
So where is the -1?
Like yeah. Here. I think for example, there are like 8 components
Ah,
here.
ah.
So you just briefly mentioned about like, for example, we use like the first 7. It's a
No, not first step, only 3. But of course, I mean, how to say, this is a kind of a criteria. So there are no specific rule how many factors we need to use.
just depends on
Yes.
the
But if you plan use the PCA, then you plan to submit your paper in the Q1 journal. Then point is that the reviewers will ask you how you can decide. I mean, for instance, I decide to use the first 4, and then he will ask you a justification. Why? What is the reference? What is the criteria? So actually, no answer. But normally, if we have this one, Kaiser criteria, then it is okay. I mean, I cannot say it should be, but I can say we normally do. Okay, yeah. Ah, okay, so okay. So I can just turn it off. It's okay. So for instance, after this class, I will just close it. I mean, turn it off. So it's okay. How close it? Just leave. Okay, I see. No. Stop recording. That's all. Okay, I see. Okay, I see. Okay, I see.
some similar exercise, similar to English.
Because I didn't decide yet. The quiz, I didn't make a quiz yet, so yeah. But maybe you can find some textbook, maybe similar.
Okay.
Okay. Yeah. Oh.
Okay, so let's start the second session. So second session is about the factor analysis. Factor analysis is, I mean, concept is very similar with the principal component analysis. Okay, but it's how to say, more statistically better or advanced than principal component analysis. Okay, so before I start, maybe I can start from the comparison between what is the PCA and what is the factor analysis. I mean, factor analysis is also concept is very similar. There, I mean, the something like clustering. For instance, here we have 6 different observation variable: x1, x2, x3, x4, x5, x6, and then we gather similar things there and then collect a new variable here, z1, z1, z2 there. But in terms of the point, the academic point, what is the difference in the PCA and the factor analysis is that even though they cluster the similar observations together, PCA is more like a clustering purpose. I mean, divide the observations, similar observations together. And then factor analysis is more about the constructing the new variable. So PCA, of course, the paired components, we can say this is also new variable, but statistically, the Z from the factor is more robust. Okay, so if you want to create a new variable based on the correlation between the observed variables X, what I suggest you use more is about the factor analysis. This is the we normally use in academics. Okay, so here the nature PCA is more about the clustering, the dimension reduction, clustering. But what is the purpose of the factor analysis? We directly use the statistical model. Y equal Y equal beta 1, Z1, beta 2, Z2, like this, something blah, 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 okay? So this factor analysis is combined to the structural equation modeling today. I mean, I will explain you later here. So something blah, 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 explanatory blah, blah, and I will explain you one by one. So this is the concept, basic concept, why they developed the factor analysis. And then based on the observed variable, we derive the factor. So concept is very close to the principal component analysis. So factor analysis aims to explain correlation covariance among many observed variables, x1, x2, they observed, then we create z1. Okay, and using a smaller number of observable factors and reduce the p observed variables in the k latent factors. So very similar with the PCA. And the core idea, most of the shared variance among variable is due a few underlying common causes factors, something like that. And then factor analysis is still about the variance. Again, variance means that N1, and your data, N1, N2, N3, blah, 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 and here X1, something, blah, blah, 5, 3, 4, 7, something, blah, blah, blah. Then in this case, you can split, you can spot the X1 for the observation, something like that, something, blah, 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 blah. Okay. And then in this case, how we consider the factor in the factor analysis is that the variance difference between the observation and the mean. So it's very general concept here, right? And then this is the kind of the regression linear relationship with the error. Okay. So here, mu is the mean, and this is the observation. F is the common factor, latent, something blah, blah, blah. Okay, so we derive how to F there. Okay. So common assumption is similar to the PCA. Factors are uncorrelated with each other. And factors are uncorrelated with the errors. It's very similar with the regression model. The errors are uncorrelated with each other. Okay. Blah, blah, blah. And then here, there are two techniques. Orthogonal factors and the correlated factors. Orthogonal, you can imagine, they orthogonal like independent. So here in this figure, this is the orthogonal. This is the orthogonal factors. How we know they are orthogonal? Because they are including. So these three factors only including this factor. These factors only including this factor. Okay, we arbitrarily separate them factors, but of course in reality, for instance, for these three observed variable, it can be like this. It can be like this. It can be like this. Of course, I mean, this is possible in reality. So in this case, this is the correlated factor. Okay. So orthogonal factors, correlated factors, they are, this is the difference. Okay. But in reality, normally in your data, which method is normally better? This one, more accurate actually. But what is more popular? This is more popular. Independent. Why? Can you imagine? Here, computational burden. You can imagine there. If we have many arrows like this, it's more difficult to calculate. So therefore, there are some computational burden. And then, especially in academic research, can you imagine why researchers do not much use the correlated factors? Can you imagine? Especially if you are in LSGI or BRE or BEEE, maybe your research may be close to this analysis, can be. Then normally, I also, when I conduct similar analysis, I recommend to do the orthogonal factors rather than correlated factors. Why? And not the technical reason, another reason, empirical reason. Can you imagine why? The interpretation is more difficult. I will explain you later, but after, I mean, this figure, for instance, this is an example in social science, maybe I remember. So here, these three features, are clearly related to the one variable in orthogonal clustering. So it is very easy to make a name. Its name, new variable Z1. It's not difficult to make a name. We can just think about the generalized name for these three factors, right? Also here, for the food quality, the naming is the food quality here. This is the latent, they are latent. But here, how we can decide the name of the latent variable Z here is that we consider generalized name, taste of food, food temperature, freshness of the food, something like that. We just consider the generalized name for these three factors. That's all. But you can imagine in practically, if you use the correlated factor, then it's something like that. Then, okay, I mean, statistically, it's okay. I mean, we can generate the new variable. For instance, let's assume just we consider 5. Oh, not last one, just for the 5, this one. And then what is the name of this one? How we can interpret this new latent variable? So many in reality is very not easy, very, very difficult. So even though it's a correlated factor are statistically better, if we cannot make a contribution based on this factor, then why we need to use in our research? Actually, no contribution there. So normally, I mean, I cannot say definitely we should do. I do not mean, but in reality, in many academic paper, we normally more prefer this orthogonal factor, independent factors. Okay. So orthogonal factor, the Z1, Z2 are uncorrelated. So there are some concept of the rotation. Rotation means that 3-dimension, multi-dimension, we just rotate it, but it's out of the scope in this class. So just you use something blah, blah, blah. Normally how you do, you normally make a code, or you can just use the SPSS or MATLAB. There are some code, but at least you can easily, what you need to remember, there are some 2 different techniques and what is the pros and cons of each one. Okay. So the correlate factor, of course, I mean, is more better, more mathematically more better. So some common rotation is about the here the orthogonal cases is the very max, is a kind of a statistical rotation method. But the correlated factors, Promax and Oberlevin, but normally we use the Promax rotation algorithm there. Okay. So here, this is the point. Most important thing here in this slide. So correlated factor is better than orthogonal uncorrelated factor, more realistic, more accurate, but the interpretation is very difficult. Something there, but we cannot interpret it. So, but it's useful when theoretical constructs are expected to be correlated, something like that. Okay. So what do factor loading mean? Is that factor loading here means that some coefficient here, for instance, I will show you some example table. We will have some kind of parameter here, lambda 1, lambda 2, lambda 3, like a regression model, the parameters. And then we need to interpret it. So how we can interpret the factor loading the parameter? So the correlation between observed variable x and the latent variable f. So x1, z1 or f1 or whatever. If it is 0.5, it means that the correlation between x and f is 0.5. Okay? So how we, I mean, of course, there are no rule. Rule of thumb is that maybe you know this terminology. It's about the heuristic. I forgot the some heuristic way. So normally, once you prepare your publication, so how you can interpret the factor loading result is that we just normally do, if it is 0.7 higher than 0.7, we assume it's a strong relationship. between X and F or Z, whatever. And then if it is 0.4, 0.6, it's a moderate, so. I mean, it's not much good statistically, but we can still use it. But if it is lower than 0.4, in this case, the result I suggest not to use for your final result. It's a weak, statistically weak. So in this case, you can just say, oh, this value is okay, so I use it in my analysis. Then Libio will be okay. But in this case, if you use it in your analysis, then Libio will attack you. Okay, he will ask you your justification. Okay? So order rotation, blah blah blah. And then the how to interpret factors. I mean the F1, F2, same again, the naming. So look at the variable with the highest loading each factor. Okay? Identify what these variables have in common. Common means that generalization. And give the factor a theoretically meaningful name. So if the loading is like that, comfortable, convenience, flexibility, and privacy. And then what we normally do, we try to generalize the name. So actually, it's empirically sometimes not easy. But these days is much better. Why? Because you can ask AI. Right? So this one, what is the generalized name? Something like that. So it becomes very easier. Okay, so it can be the preference for the private mode, something like that. And then also another example. This is the X5, X6, X7, something like that. Environmental concern, willing to pay more, support for the transit, then name could be the pro-environment and the pro-transit attitude, something like that. Okay? So there are no answer actually. You just need to justify your decision. Okay? So this is an example for the factor analysis there. So here, the question, for instance, for the quiz, this is the result of the uncorrelated factor loading or uncorrelated factor analysis or correlated factor analysis. Uncorrelated or correlated. Oh, no one? Correlated. Well, why? Because it's still number there. Okay, uncorrelated. If you use the uncorrelated, they should be nothing. Because we already assume, I mean, strongly confirm this one only for the factor 1, this one only for factor 2, something like that. We already decided. But this one, every variable influenced every factor. So something like that, 1, 2, 3, 1, 2, something like that, right? They are already correlated, even though the number is small, but at least it shows that the factors are correlated. Right? But in this case, then how we decide the name? So it's not easy, but luckily, if your result is good, then we can consider the highest value there. Okay, then we can clustering there, and then based on these highest effects of the variable x, then we can try to make their name there. So if it is good, I mean, if you are lucky, then sometimes it's okay to make a name. But sometimes it's not easy, many times in reality, because X is quite different. Okay, and then here, another question. Then, okay, so I see the number of factors, factor analysis, like a PCA, they will give me the result. Then can I use everything? Everything you can use, but normally what we avoid is that it can make make your parameter estimate biased. So, I mean, no answer. This is also heuristic. This is not statistical decision. Heuristically, I mean, in the academic paper, we have some several index there. But similar to the PCA, we normally use the eigenvalue, same. The eigenvalue is larger than 1. So I cannot say this is the best way. I cannot say statistically. But I can say once you submit your paper in the journal, this is the most safe way. It's not best, but the reviewers will accept it. Okay. Okay, so practical steps, how you can do practically in your data. We first theoretically justification. Who do we expect latent factor? Okay. Then we check the data suitability. I mean, is it still the data is good or not, something blah, blah, blah. And then choose the number of factor based on the factor analysis. I mean, eigenvalue is larger than 1, or screen plot, or parallel analysis theory. If you say, oh, I mean, for instance, here, if you want to only 3 factor, eigenvalue is larger than 1, but the first factor, I still want to use it, but their eigenvalue is lower than 1. Can I do this? You can do, of course, because this is the heuristical way. But what you are required is that you need a justification why you use. So normally it's not easy. So you have some, based on theory, this should be included. But even though eigenvalue is not is not larger than 1, it is still theoretically important factor. Therefore, I use it. Okay. But for the reviewers, it's not easy. Okay. Something like that. Okay. So, and then extract the factor or something, blah, 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 and the rotate factor, interpret the loading and the name factor. This is the major work in the factor analysis. I mean, once you data, analyze your data based on factor analysis. I mean, factor analysis is not difficult. I mean, everyone can do. Even though if you install the SPSS, you can just click, and then you will get the result. Okay, everyone can do. But what is the most difficulty? What is the most how to say? What is the challenge to decide your result is that here? The interpretation in reality. Your data is not always ideal. So the factor analysis sometimes is crazy, really crazy. And then if you cannot naming, then you cannot use the result. I recommend you not to use the result. Okay. So then how you need to do a trial and error. You need to cut some ideal observation. I lectured in first lecture or second lecture, right? Week 1 or week 2. You need to cut some ideal values and then rotate it again. If you have some ideal theoretical framework, then your result should be more robust there. Okay, fitting more with the theoretical framework. So normally it's not easy. I mean, I have data. So I finish my, I finish almost my PhD work. I get the data. No. Your data normally is not good. Okay, you should remember. Of course, I mean, I cannot say, okay, I have many times when I talk about it, I mean, the data cleaning, I do not mean, for instance, if you have 100 observations, I do not mean cut 50 observations. This is not the data cleaning. Data cleaning like 10%, lower than 10%. My point is that. But still, we don't know which observation makes some problem. So you need to, theoretically, you need to conduct many statistical tests to check your data. Okay, so something like that. Okay, so this is about the factor analysis. So any question? Okay, so both of them, factor analysis and the PCA, their purpose is same. But what's the difference is that Difference is that PCA is more like clustering. Their statistical background is not strong. Vector analysis is more strong, but it's more complex, of course. Okay. And then the today main issue is about the structural equation modeling. So maybe most of you are familiar with this name. I mean, structural equation modeling called the SEM. It's really widely used in any, I think, any engineering area. This is the, how to say, very, very basic. So especially SEM in the environmental engineering, SEM in the urban planning, many urban planning, also geography, also. And what else? Civil engineering also, we use many times SEM. Okay? And built environment, whatever, something blah, blah, blah. So here, compared to the factor analysis, SEM include the factor analysis. I'm sorry, it's reverse. Something like that. So you can easily assume that, I mean, not exact, but for the better understanding, how you can understanding is that structural equation modeling is the factor analysis today you run plus regression model. So this is more comprehensive structure. Okay, so theoretical background, I mean, again, I mean, today, once you have your data, when you analyze it, y equal fx, it means that x influenced y. So this is the basic scientific assumption. But of course, in the long history by Albert Einstein, one of the important issues is the causal relationship when we make an equation. Okay, so equation, we first decide to y, but y should be influenced by x. But many scientists over the civil engineering or engineering field, I mean, all the academic field, major assumption, what happened there? Why you decide x influenced y? Right? This is the very, very philosophical question. Okay? So based on this, I mean, structural equation modeling is the most flexible, I think. I mean, of course, in the statistics, machine learning is more flexible these days. So normally, I mean, we have a regression model and the many advanced regression model. But why researchers enjoy to use the structural equation modeling? Because very flexible. Very flexible. Very flexible for what? Between the relationship variable x1, x2, or x to y. Very flexible relationship. So SEM has been widely used. But of course, I mean, this flexibility is based on the statistical field. So if we do more, machine learning is more flexible. It's the data driven. Okay? So SEM, so far SEM as a concept is a combination of the statistical technique, factor analysis, and the multiple regression. Okay? So why? Because the SEM is based on two-step measurement model and the structural model. I will explain later. So the purpose of SEM to examine a set of the relationship between one or more independent variable. And then this is common, I mean, other statistical model. But here, this is the point. One or more independent y. Y can be 2 or 3 or 4, whatever. Very, very flexible. Okay? So structural equation modeling is a comprehensive statistical framework. Comprehensive means that flexible. Designed for complex, flexible, real-world social behavioral phenomena. Okay? Especially useful in transportation, psychology, social science, marketing, urban planning, geography, something like that. And then structural equation modeling is also known as a causal modeling. Causal, x, y, y, x, this is the causal relationship. Okay? Or analysis of the covariance structure. This is based on the factor analysis. So path analysis are confirmed factor analysis are special type of the SEM, actually part of the SEM. So what problem does SEM solve latent variable, identify latent variable? I mean, based on factor analysis you run, right? And then measurement error in observed indicators. And the endogeneity is about, they are both about actually LV. The complex causal structure and the variables that are both causes and effects at the same time. SEM, structural equation modeling, we can formulate this relationship together. It's not possible in regression model. Okay, but SEM is possible. Okay. And then core component of the SEM. So here, two main parts. First, measurement model. Measurement model means that measure something, right? So factor analysis. Here we use. Factor analysis is a part of the SEM. And the structural model is called the path analysis based on the regression model. So it specifies the causal relationship among latent variable. And then it can also include some observed variable. I will show you example one by one. So here, based on two things, I first introduce about the structural model called path analysis. It's not equal. Actually, one kind of structural model. Okay? There are many, of course, possible structural model, but path analysis is the most basic. Okay? The path analysis, so name itself everything. Analyzing path. What is the path? This is the path. Okay, relationship. The path analysis is like a relationship analysis. So it examines how independent variables are statistically related to the dependent variable. Okay, and then applies the technique of regression analysis, aiming at more detailed resolution of the phenomena under investigation. And it allows the causal interpretation of the statistical dependencies and the examination of how data fits with the theoretical model, blah, blah, blah. So it's very common things. So process. Once your data is prepared, conduction of path analysis is straightforward. So draw a path diagram according to a theory. Theoretical background is always easy to be justified. Okay? And then conduct one or more regression analysis. I will show you example one by one. Okay. So compare regression estimated beta, the theoretical assumption or other studies, something blah, blah, blah. If needed, modify model by removing or adding connected fact, path, something blah, blah, blah. So here, data assumption again. So dependent variable y, independent variable x. So y should be continuous. Okay. So it normally distributed. Normally distributed means that this is the y, and then it follows the normal distribution. So this is the what I lectured in first week one, normality. Okay. So normality. Okay. X, independent variable also need to be continuous. So here, data assumption. So theoretical assumption, causality. X1, Y1 correlated. What it means that age, income, you can think about this for each people. Normally, I mean, not exactly proportional, but normally we can assume age is higher, then income should be higher. Not exactly, but they have a very strong relationship, right? Maybe under 65%, right? So here, X1 proceed Y1 chronically, and X1, Y1 are still after controlling other dependencies. So in this case, we can assume age and income, theoretically or reality, they should be correlated, right? And then statistical assumption, model needs to be recursive. I will show you the example. It is okay to use the ordinal data, and all variables are measured without measurement error. So this is the most challenging. Okay, but yeah, still we can use it. So path analysis. Path analysis assume that model is recursive. Okay. And then nature of the causal dependency is unidirectional, like a one way, something like that, X, Y. But what is the good things is the path analysis. If we have some pre-information, theoretical background, we can decide the relationship. But if we don't have it, if there are no primary information, we don't know age, gender, age, income. Which one affects the other one? We don't know. Someone can say age affects the income, or the other say, oh, income affects the age. I don't. Maybe just us. We don't know. Okay. Then in this case, we can use the two-way arrow, and then we can test it using the path analysis. Okay? So here, this is an example. Age, education level. This is the willingness, and then this is about the task, just for example. And then we assume age affects their amount of the task, and then education level affects to the amount of the task, and then their willingness to work, their affects to the task, and then we also assume that their education level affects the willingness, their willingness to work, and then education and age, they are intercorrelated. So in this case, it's more like a social science, but in this this naming itself, but you can say this structure is not possible in the other regression-based modeling, right? Especially here, moderation, something like that, and the interaction is not possible in regression model. So this is the property, I mean, the strong advantage of the path analysis. Okay? So here, we assume that direct and indirect effect. Indirect is about the moderation. So age influence the task, direct. Nothing in middle. Education influence the task, also direct. Willingness affects the task, also direct. But here, education affects the task through the willingness. This is the indirect, right? And then here, path analysis. To conduct the path analysis, we first need to identify two things. So normally they use exogenous, and endogenous variable, but you can just easily assume endogenous is the Y. I mean, dependent variable. Exogenous is the X. Okay? So outgoing errors, XY, and then this is the exogenous. And this is the endogenous. Okay? Exogenous, endogenous exogenous variable, endogenous variable, this is quite general in the SEM studies. Okay. And then path analysis. So in this case, we can assume age, education, it can be even willingness, it can be exogenous. But task and the willingness, it can be endogenous. Task is clear. Why willingness? Because this error. Okay, willingness influenced by education. Therefore, willingness also can be the endogenous. Why? Okay, so in this case, for the path analysis, what we need to do, I mean, analysis, the way of analysis is very simple. So we just estimate the two regression model based on different endogenous variable Y. So why? Because here, in this case, we have two different endogenous variable. So for the path analysis, we conduct two regression analysis. So here, another example here, this one more simple. So this is the X1 is the educational level, and then X2 is the salary. X3 is the times, I mean, the amount of the drinking the decaffeine coffee. Okay, very simple. So we can assume that education level and salary significantly influence their amount of the drinking decaffeine coffee. But also education level can influence their salary, of course. Okay? So here, I mean, this is an example for the path analysis. So here we can imagine So in this case, for your quiz, I can ask you. So this is my plan for the path analysis. Okay. So how many endogenous variable here? What is or what are the endogenous variable here? Two. Decaffeine of coffee and the salary. Okay. It's very basic level, right? So it's not so you can conduct the two regression analysis. Decaffeine coffee equal beta 0, beta 1, education, beta 2, salary. This is first one. And the second one, salary. Beta 0, beta 0, beta 1, education. Okay. And then this is the example file based on SPSS. SPSS is the most basic software for the statistical analysis. So I think it should be available in the PolyU also. So here, I mean, this is the data. Okay. So X1, X2, X3. And then this is the observation. 1, 2, 3, 4, 10, blah, blah, blah. Okay. Here, first analysis for this one. This is the result, regression. So adjusted low square, you run it, right? Low square, adjusted low square. Okay. So adjusted low square is higher than 0.8. So its explanatory power is really good. Why? Heuristically, if it is 0.2, it's okay. Okay. And then here you can see this is the beta. But path analysis, one thing we normally use the standardized coefficient beta. You should remember what it means, right? It's week two or week 2, I remember. So I explained what is the standard coefficient beta, right? So this is the normally path analysis. We use the standardized coefficient beta. So you remember why? Why sometimes researchers prefer standardized coefficient? Why researchers prefer this one rather than this one? Oh, yes, different unit. Their unit is different, so we cannot compare. I mean, comparison, this value, comparison, this value, it does not mean anything. So it's just number. So interpretation actually is not easy. But if we make it standardized, we can directly interpret the result. So for instance, here. So here, I can ask you, so okay, this is my result in the regression model. So now I have two different variable. So between two different variable, in terms of the unit variance in the standard deviation, which variable has a higher, more significant influence to Y, the decaffeine coffee? Which variable? Education or salary? Salary. Why? Standard beta is the absolute value of the standard beta is higher, larger, right? So you can see the result is reversed here. So if we only consider beta, actually this one is much higher. The education level is much higher, beta. But point is that salary is maybe $1 Hong Kong dollar per month, maybe. And then education level is just a level. So we cannot compare this one. But with the standardized beta, we can directly compare them. So we can see now this is the larger than this one, right? The relationship is reversed. So in the path coefficient, I mean, of course, I mean, there are no exact answer, but academically, if we look at the published paper, normally we use this one, standardized beta. Okay? So this is the result of the first one. First result, this tape. This table result of this one. Okay? And the second table is the result of this one. So in this case, we can conduct regression analysis 2 times for the path analysis. And then here, education level salary is the standardized beta here. And then here, this is the result of the path analysis based on this data. Okay. So what it is, 0.51, 0.52 here. Okay. So so 0.18, 0.2 here. And the 6.7 here. Right? And then what this value is the adjusted rho square. So, I mean, this is only 3 variables, very, very simple. So this is the result of the example path analysis. Okay. So you remember here, we have a R square here, but we normally use the adjusted R square. Why? R square is more historical background, but we normally technically use the adjusted R square. I can ask you in your quiz. Okay? Why? Yes. Yes. More variable. Then even though the explanatory power is not different, but R square automatically increasing. So it's not good. I mean, it's not good compare models or interpretation of the model prediction power. So we normally use the adjusted R square in the regression model. But of course, I mean, recently we also used AIC, BIC, something like that. But it's out of the scope in this class. I mean, so adjusted R square. So it's in the lecture file, right? Okay. So this is about the path analysis. So I mean, this example is very simple. So we can easily discuss in the lecture. But you can imagine if we have a 10 variable, 20 variable in your data, then the paths, there are lots of paths there. And then many possible endogenous variable Y. In this example, only two endogenous variables here. So we can only need to conduct 2 regression analysis. But in reality, for your journal publication in Q1 journal, then I think you need to at least more than 10 times regression analysis. 10 times even is not enough. I mean, variable will be very big. Okay. So normally, so it's also kind of some trial, not trial and error. It's consume much time. Okay. Oh, so any question about the path analysis? Oh, so it can explain the relationship between variable. Okay, so in this case, so so this one is the purpose. So we can understand how each variable influence to the other variable. So even, I mean, this one is the very simple. So maybe the contribution looks not much significant. So only 3. So, but especially this relationship is quite new, not possible in the regression analysis. But in reality, sometimes it can be also reverse, something like that. So in this case, this is our ultimate goal, is your topic, and they are X. Actually, we can identify the complex relationship between different X, how they ultimately influence over the Y. Otherwise, if you just your regression model is like this. Right? This is the X1, X2, X3, X4, X5. We only identify this relationship mathematically. This is the regression. But it assumes they are independent, perfectly statistically independent. But your data may be more like this. Then how we decide to justify this relationship? And of course, even though you conduct the past analysis, I cannot say this relationship is the best. Is the best relationship. But at least I can say this relationship you can justify statistically. Okay, you can say this complex relationship I found, and then it can be acceptable in academic society. So compared to this one has more complex relationship. For instance, here, if you just use the regression model or just a linear model like this, you can only identify these effects, right? So you can assume, okay, the education level for the decaffeine coffee, they have the influence like a 0.51 based on the change in the standard deviation change there. But you can see they are also indirect relationship. In this case, how we calculate, I mean, I do not prepare it for this class, but normally directly here, direct influence 0.51 education level to decaffeine coffee. Here, indirect influence 0.39, 0.52. Okay, plus this is the influence about the unit change of the education to the decaffeine coffee. But in the regression model, linear statistical modeling, we normally ignore this one. Then it can be maybe 0.57, something like that. So the result, we can say this one is more correct compared to the regression. This is the purpose of the past analysis. Okay, it's okay. And any other question also? So past analysis is the part of the SEM. So after past analysis, we also need to a regression model. So I will show you more. I mean, okay, then let's move to the constructing SEM model. So based on the past analysis, we can construct the structural equational modeling. Okay, it depends. I mean, if you have a many X in your data, only using past analysis, you can publish even your paper in good journal if you have many X there. But if your data does not have many X, only past analysis is not enough. The contribution is not much enough to be published in the Q1 journal. Okay? So in this case, you add more and more contribution, more analysis. Okay? So in this case, SEM. So SEM normally one of the most well-known covariance structural model is called the Russell. Maybe you heard about this if you are working on it. Okay, so it's like a linear structural relationship. Okay? So here. Maybe I can explain you right. So Russell is like a path analysis, but it's a little bit more advanced, in my perspective, a little bit compared to the path analysis model. So here, Russell, even we have a software, okay, something like this, and this is very popular, Russell, Amos, or something like that. So normally, I mean, if you want to analyze your data based on SEM, because SEM is very complex model, so making code is possible, but I believe in the PhD level it's not easy. Making code using R or Python, maybe some library code maybe is available, but not easy because very long. So how normally PhD students do when they analyze their data using SEM, structural equation modeling, software, specific software called Russell or Amos. Amos is the most famous one. So Amos is kind of how to say, kind of additional package in SPSS. I mean, it can be added in SPSS, but in the university version, general SPSS, there are no Amos there. So normally we purchase the Amos package from the company and then install the Amos in the SPSS. So, but it's too empirical issue. So, and also M+, this is the most famous. I normally use the M+, my students. And then model constructing, the latest software, SEM, graphically intuitive, Amos, blah, blah, blah. Sorry, it's duplicated. So model constructing. So for the SEM, what we normally do. So normally first do hypothesis. So if we don't know, we first do hypothesis. And then we check whether the null hypothesis can be rejected or accepted. You know what it is, statistical inference, right? So we just test H0 can be accepted, can be rejected or not. We just test. Okay, then based on this, we have a model specification. And then the identification and the estimation. Okay, based on estimation, we decide the hypothesis can be H0 can be rejected or not. Okay. So here, example, the measurement model. So here again, SEM. SEM is you can easily imagine, as I show you, factor analysis plus regression model. Okay. Now, where it is? So therefore, basically, it constructs based on the two model, measurement model and the structure model. So I first explained the structure model, regression, path analysis, and now is the second part, measurement model, like a factor analysis. Factor analysis, I confirmatory, explanatory factor analysis there. So I mean, the name is different, but the same concept. Confirmatory. Yeah. So as I explained you, there are two types of the factor analysis, correlated and uncorrelated, right? So you can see, you can infer based on the name, confirmatory. This is the uncorrelated or correlated. Confirm. First decided. So uncorrelated. Why? Because X1, X2, X3, X4. So here I first decided, okay, you go there, Z1. U, go there, Z2. This one, no, not allow. I confirm first, confirmatory. Okay, and then second one, explanatory. You can imagine uncorrelated or correlated. So it can be like this, everything. So explanation is better. Okay? So here, let's return here. So this is an example of the measurement model. So this is the confirmatory. So correlated or uncorrelated, right? So name itself, confirm. Okay? So you can see different factor influence to the different latent variable, right? So, and then here, this one, possible correlation. Okay, we can also calculate the possible correlation. And then model specification. Specification of the confirmatory factor analysis or model, whatever, requires making formal and explicitly stated about the number of common factors and number of observable variable X, the variables and variances and covariances among common factors, the relationship among observed variable with the latent factor, the relationship among the residual variable error term, it means that error term, and the variance and covariance among the residual variables. Okay, so here we can see model specification. So yeah, I mean, let's try one by one. Model specification by describing factor equation in two-phase model in this case. So here, this latent variable influenced by this 3x explanatory variable. So in this case, we can just directly use the something like this. Okay, so here, first model, I don't know how to pronounce this letter in Greek, but here, these are about latent variable 1. And then this one available for the latent variable 2. Okay, so X is observed. So we know what is the value. And then the theta error. Okay? And then this is about the kind of regression model, right? So we have a six independent variable X, therefore we have a 6 linear regression model. But how it can generate the how it can be generate the latent variable, because for the X1, X2, and X3, they share the same explanatory variable, the latent variable 1, right? Therefore, we can assume X1, X2, X3 are correlated, not independent, right? So let's return. I mean, return to first. So again, I mean, in the early of this lecture, so what is the today lecture? I mean, let's recall the purpose. So this is our data. I mean, any data, the general data format. So here, I mean, so far, week one is the probability. Week 2, week 3, part of week 1, you learned about the regression model, because regression model is always the basic, the best, I mean, most common. But in my data, so if you have a data like this, you can just use the regression model. But what is the problem there? I mean, many assumptions can be violated. So what is the most common assumption can be violated is that collinearity. Okay. So this is the lecture file last week. And then what multicollinearity means is that they cannot be independent many times. I can imagine most of them, the variable in your data cannot be independent. Okay? So in this case, then how we can analyze, I mean, regression model we cannot use anymore. So what is the idea? Is that we can collect some more correlated variable together. So based on this one, latent variable Z1, Z2, Z3. So if we do like this, what is the implication means that X1, X2, X3 are correlated, not independent. Therefore, the latent variable Z1 can consider the correlation between X1, X2, X3. Right? So this is the basic idea for the latent variable model or structural equation model, whatever, for the latent variable. So here, return. So this is the core. So here, so far, you can see this latent variable now itself, it is including X1, X2, X3. Therefore, you can see this latent variable consider correlation between X1, X2, X3. Okay, why? Because it's included in the X1, X2, X3. And then how to capture the different correlation in each variable by the parameter, different parameter. Higher parameter value, absolute value of the parameter means that X1 is more, has a higher covariance, correlation between other variables. And then set lambda 2 is lower, absolute value is lower, means that X2, the correlation between X1 and X3 is lower than other variable, something like that. Okay, so this is the basic idea. In this case, we can construct a 6 regression model for the 2 latent variable. Okay. So here, most of calculations are performed. I mean, this is the general, but you see if you are familiar using the MATLAB or some Python, I don't know. I normally use the MATLAB or R. So Python, I'm not sure. But if you normally make a code, then, I mean, this is okay, but we normally use it based on the matrix. So so this is the okay, and then in the matrix form, it's like this. Okay, I mean, same thing, actually it's same. Then why we make it actually for the coding? Better for the input coding in the matrix form in the MATLAB or some R or whatever. So here, I mean, same. Only we have a generalized formulation and only put 0 if the explanatory variable X is not correlated to the latent variable. Okay. And then this one, of course, mathematically in vector form to decrease the amount of the equation. So this is the how to say matrix form of the equation. Okay. And then if we solve it some mathematical way for the vector formulation, it's like this. It's like this. So this is the how it work in the Amos program software. X1, X2, X3, X4, X5, X6, and then 2 different vector, 2 different metrics there. And then plus here, something blah, blah, blah. This is the error. Okay, so this is the formulation, how software, statistical software conduct the measurement model in SEM. Okay. So of course, I mean, if you use the software, you can easily, I mean, the click, that's all. But if you want to make a code by yourself, then you make a code like this, okay, based on the matrix form. Okay. And of course, also covariance here. This covariance can be also formulated in the matrix form like this. So variance, covariance matrix. Then it's okay. I mean, just for your information here. Okay. So function. So here maybe I can explain you more, little more. So this one we have two. This is the two. Maybe later. I mean, it's maybe too difficult. So anyway, I mean, in this case, we can estimate the covariance here. I mean, something blah blah blah. Okay, so it's based on the variance covariance matrix, but if I explain variance covariance matrix, then maybe the time is enough. It's not enough. So just to assume that, okay, based on the mathematical modeling, based on the variance covariance matrix, blah blah blah, and then we can identify the covariance, something like this. Blah blah blah, and the equation has something blah blah blah. So in this case, based on the variance covariance matrix identification, we can calculate it. And what else? So then let's talk about the estimation, more about the estimation. So far, I mean, in this class, I mean, of course, there are lots of the advanced estimators, but especially in the regression model, I only teach about OLS and the MLE, right? The estimator. So in the regression model, what is preferred between them? A regression model, OLS, is the most basic. But what is the assumption? So you should remember, based on what assumption MLE estimator is equal to OLS estimation, OLS estimator. In lecture 5, I show you they are same, results are same. What kind of assumption? It's about the error, residual, IID, right? IID in the error terms should be identical and independently distributed following normal distribution. So in this case, they are same. And then, so in this case, they are same. Then why researchers prefer OLS estimator for regression model? Why? Biased, right? So OLS only consider OLS only consider the difference between y minus y hat. We only consider this one. So OLS estimator, it can say unbiased parameter, right? Beta can be unbiased, right? MLE estimator, beta also unbiased. We can say MLE estimator, beta is unbiased. I explain you, right? The population beta is same, unbiased. Then what is the problem? MLE. Oh, they are same, unbiased parameter. Then I can use MLE. Why still researchers prefer OLS? The variance, you remember. Variance can be biased in the MLE estimator. Variance of beta, the error variance of the beta can be unbiased. But if observation is larger, then it can be unbiased. It's the lecture file 2. Okay, so this is the kick. So it is, I mean, OLS no variance information there. So only beta there because only this information. So beta, mean of the beta, expectation beta is unbiased. That's all. MLE estimator, expected beta is unbiased. It's okay. But the variance of the beta can be biased. So OLS estimator is more reliable. Okay. Then you remember. So OLS estimator in the regression model, OLS is preferred than MLE. But when MLE is more preferred, I show you in the table. So what is the assumption in OLS? IID. If IID is blocked, then we cannot use the OLS. Why? Beta is biased. Mathematically, if we calculate expected value, beta become biased. So if we can say error terms are not IID normal, then we cannot use the OLS estimator anymore in the regression model, even in the regression model, whatever. So normally we use the MLE, but you can imagine most of your data, we can, I mean, even though we do not prove, but we can imagine IID is very, very strict assumption, right? So if you use the data in your data, normally, I mean, at least in the PhD level, OLS cannot be useful. Okay, why? Because simple regression assumption can be violated. So normally, I don't know how much you deep inside in terms of the statistics in your PhD work, but normally you should start from the MLE estimator in your analysis, because I can imagine your analysis is not about simple regression. PhD level simple regression is not allowed. PhD thesis for PhD thesis. Then you may use some advanced statistical model. Then starting point is always MLE. It's more flexible. Right? So here you can imagine SEM also. What could be the estimator? OLS or MLE? MLE. Right? MLE is always the basic for the other advanced model. But of course, MLE is not the state of art. But classical is the MLE. But it's not much flexible. Why it's not much flexible? What is the always, I mean, any model, regression or discrete choice model or some other statistical modeling, once we use the MLE, what is the problem? MLE estimator, maximum likelihood estimator. Likelihood estimation is very mathematically useful, but what is the issue? Identification. What is the identification? If a researcher too many parameter, if you use the too many parameters in your model compared to your number of variable, then no value there. So your software will say, oh, no identification. Maybe I can show you some cases. Something like I don't know how the researcher estimate the model, but let's assume A is our estimation. Then many times, if your parameter is too big, and then they say NAM, nothing. This is very common for the MLE estimator. Why? It means that your your software, MATLAB, R, or whatever, they cannot identify your parameter. So in this is actually problem from the MLE estimator. Okay. So here, I mean, I will explain more details. I mean, so at the PhD level, so my data is not proper to use the MLE estimator because I try to estimate the model, but the many parameter is non-identified. So it's problem. Then what can I do? So I'm not sure I can teach it in this class or not. But one of the answer is that Bayesian estimator. Bayesian. Maybe you heard about the name of the Bayesian, what it means. It's a Bayesian estimation is not machine learning, but in my knowledge, in my perspective, is in the middle to go to the machine learning identification. Okay, so Bayesian estimation, it is free from the identification issue. It can estimate the model if you ask many parameters, if your data simple, but if you ask the many parameters, estimate the many parameters, Bayesian estimation is normally okay. So PhD level, if you want to go deep inside, then Bayesian estimation you need to study. But of course, mathematically more complex compared to the MLE. Okay. But anyway, I mean, so return to the MLE. So what is the conditions for the, I mean, to avoid the identification issue? I want to estimate my parameter in the SEM. Actually, it's more for the MLE. I mean, any statistical model for MLE. There are some necessary condition and the sufficient condition and the necessary and the sufficient condition. This should be satisfied when you estimate the model. So necessary condition which are essential but not sufficient. Sufficient condition which if meet the imply the model is identified, but if not meet do not imply opposite. Okay. So model specification, necessity condition, if simple to test, since it relates the number of independent covariance equations to the number of independent parameters. So for instance, I mean, for PhD students here, I mean, of course, I mean, your aim is to publish the paper in good journal. So good journal always requires more and more. So problem is that, I mean, simple model is not possible. I mean, if your data is good, then it could be possible. But normally, if your data is normal, I mean, not much new, then just a simple analysis, classical analysis is not easy to be published in the Q1 journal for PhD students. Then what is the way to normally PhD students do a more complex model specification, complex, more and more, estimate the parameter more and more, estimate the parameter more and more, then interpretation more and more, then contributions can be more and more. It's okay, it can be acceptable, but you can face with the identification issue. If your model is too big, your data is small, but your model is too big, then parameters cannot be identified. Okay. So covariance contains, I mean, here, for instance, let's return the equation. So for instance, here, just for your knowledge here, there are some independent equations, number of independent equations, let's assume. And then number of independent parameters, something like that. Then we have a 6 observed variable. Does distinct variance and covariance matrix here. So it's so do I need to explain it or not? I think maybe it's too deep, so maybe just skip it. Okay. So let just I want to emphasize it. What it is that if you use too many parameters compared to your data and estimation issue, identification issue. Okay, maybe the detail equation, I think it makes you crazy. So let's skip it. Okay? And then another issue in the model specification, we gain consistently unidentified model, identified parameters. Okay. If each observed variable in the model measures only one latent factor, and the factor scale is fixed, or one observed variable per factor is fixed. So identification issue is exactly here. So let's return. So here, same. This is the confirmatory factor analysis. So uncorrelated assumption. So you can see based on this equation, now we have a same variable, 6 variable, and then 2 latent variable. So only for the relationship between X and the latent variable, we need to estimate the 6 parameters here, right? So you can see this equation. So this is the observed variable, right? And then this is the parameter to be estimated, 1, 2, 3, 4, 5, 6, right? So uncorrelated factor analysis, in this example, we only estimate the 6 parameter. So MLE, 6 variable, 6 parameter is okay. But we can imagine correlated one, the explanatory. So let's assume explanatory. Then we will consider everything, right? Every possible relationship. Then number of parameters will be 12. Okay. So for the uncorrelated relationship, 6 parameter, 6 independent variable, 6 parameter is okay. But 6 parameter, 12 variable, as I explain you again, this will be more accurate, more interpretation, because we have more parameters there. So in this case, for the academic journal, it can have more academic contribution. We have more interpretation. But problem, don't. So, but why we prefer this approach is the identification issue here. The data, we don't know which parameter will be unidentified. We don't know. It's a matter of the estimation. Okay. So this is the identification issue actually. Okay, so here again. So here, each observed variable in previous example 6. So measures only one latent factor. It means that 6 parameters. Then it's okay. Consistently identified. The result will be strong. It's okay. But if not, then it can be unidentified. So we don't know what happened there. Okay? And then factor scale is fixed or one observed variable per factor is fixed. It's also 1 by 1. Okay? So this is the factor scale fixed. Yeah, something like that. So anyway, so this one, okay. So one observed per factor is fixed. Okay? So scale is about the error term, so maybe it's out of this class. So and here, when model estimation for the measurement model, when identification is approved, estimation can proceed. Okay? if the observed variables are normal and the linear and there are more than 100 observations, maximum likelihood estimation is applicable. Okay? So if not, what is the problem? Is that identification issue. Okay. So here, I think that's all. Maybe, I mean, the more detail is not necessary. So, I mean, let's do it. Okay, so this is about the SEM. Okay, so any question? Okay, so for the quiz, I will ask you, I mean, like a basic question. I mean, some of them mathematics, but it will not much complex. One of them will be complex, but any other of them is very simple equation. But I can ask you some more theoretical and fundamental question. So when OLS is preferred than MLE, then when MLE is more preferred than OLS, something when I lectured in my lecture file, everything. Okay. Okay, so and then let's talking more about the ideal, non-ideal condition in SEM. So here, again, I mean, let's return. I mean, emphasize again and again. So this is your data. Okay. So when I have my own data, what is the first option? Regression. Why? This is the most basic. Okay. So I can do something blah, blah, blah. But in reality, many times I cannot do. Why? Because multicollinear issue. They are not independent. They can be correlated. So in this case, today, I lectured to you latent variable. Something blah, blah, blah. And then you can do some SEM, path analysis or measurement model, whatever. Something like that. Then the question, so in any data, I can do latent variable. I can do generate the latent variable. Any data? Actually, it's no, also not possible. Okay, we also, even the SEM model is very flexible. But because this is the statistical model, we have a strong assumption in terms of the model structure. So still, therefore, any statistical model in the like a SEM, still something like that. This relationship still we have. Of course, I mean the SEM F is more complex. So any statistical model, because if we use the F, some framework, then it requires a strict assumption. So, but why it is useful? Because we can interpret the result academically, okay, based on this F. So this is the strength of the statistical model. But why there are so many assumptions? I don't need to want to check. And then I want to be free model. I mean, not F. I don't need F. Then solution recently is the machine learning. Machine learning does not require F. Any application for the any data, because it learns the data structure. Then you can imagine what is the limitation of the machine learning. So if we have a machine learning, we can do, right? We can just do for any data, and then we can show the result. But why? What is the limitation? Yes, interpretation. Interpretation is not clear. So maybe, I mean, if you are interested in the machine learning model, maybe you heard about the black box. Nowadays, I mean, there's still many people, many top professors, big names, they still working on the machine learning. But what they do is that solving the black box. I mean, application machine learning is not appealed to the Q1 journal these days. It's already long time, more than 5 years, longer than 5 years. So it's not acceptable now. Then what can do advanced machine learning model? What is the advanced machine learning model? Interpretable machine learning model, solving the black box. This is the state of art trend. Okay, so here let's return to the SEM. So since still SEM use the framework F structure framework, okay, we still have an ideal condition in SEM. What it is, always the distribution of the X normality, normal distribution. I mean, our data, for instance, for the X1 here, if I plot X1, then I can compare the value of the X1 across observation. But as I explained in the first lecture, based on the CET, central extreme theory, you know what it is, right? Central extreme theory. If we have a very many observations, then it follow the normal distribution, a certain normal distribution, right? I mean, CET, the central extreme theorem is the, maybe you run the bachelor, right? So I don't need to explain it. Even I lectured in the week 1, right? So in this case, we assume X1, X2, X3, all of them follow the normal distribution, X1, X2, X3. Okay, not exactly normal, but similar to normal, actually. Okay, so this is the basic assumption in any statistical model. So we say multivariate normality. It means that X1, X2, X3, each of them follow a normal distribution in data. Okay, and then functional form, correct model specification, strict F following the F, and the measurement scale continuous. I explain it, and then sample size. I mean, sample size is always larger is better. Okay, why? Because our goal is the world population. I show you population. Our goal is the true parameter beta. So if our sample is larger than larger, then our sample is more close to the population. So beta could be more unbiased. Okay? So here then, so what is the then non-ideal condition in SEM? So in this case, using SEM is not recommended. What the condition? The most common non-normality. Non-normality is that something like this, or something like this, something like that. Okay, so naturally skewed here, and the quadratic continuous was something blah blah like this. I mean, something different, and then something blah blah blah. And detection method, box plot. I mean, we just plot it. I mean, in the graph. Okay? So effects of the non-normality on SEM. So the model fit chi-square test inflated and blah blah blah. So, but what is the major issue? I told you every time, statistical modeling. So negative effect. What is the negative effect? Biased beta. Okay. Biased beta, I explain you. I mean, it's different with the true value. So it's not meaningful. Always, I mean, most common issue. Biased, unbiased, biased, unbiased. This is always the discussion in statistics. Okay. So this issue is a really problem when sample size is very small. Okay? And then severe skewness, I mean the data normality. So in this case, how to do? I mean, some advanced estimator. So I told you, I talk about the Bayesian estimator, but in statistics, actually it's not engineering field, more like mathematic or some statistical econometric field. They also use many advanced estimator, but it's very academic, mathematically specific. So I didn't show you the equation itself, but in the literature, the textbook in the regression model, this one, robust maximum likelihood estimator. So it's something about advanced compared to the general maximum likelihood estimator. So they use MLE, we use the standard estimator, but they use the robust standard estimator. So it's two mathematical issues. So I mean, just for the naming. And then another one, So distribution free estimator. So this is also quite close to the machine learning actually. So we assume that very flexible structure and fitting to the data. Okay, then this is very similar to the machine learning, the idea in machine learning, data driven. Okay? So do not assume normality, blah blah blah. And bootstrapping is more about the validation. So for the MLE estimator problem in MLE estimator, so even though my data has some problem, but I still want to use the SEM or other statistical model, then normally what I can do, some advanced estimator, robust maximum likelihood estimator. So if it is very non-normality, then we can consider bootstrapping. Bootstrapping, maybe you heard about this, right? So ADF, I mean, this is the more recently distribution free. So it is related to the machine learning algorithm, actually. Many earlier days in machine learning algorithm is from this distribution free techniques in statistics. So something blah blah blah, but I mean it's too deep. I mean in this class, out of scope. So and then sometimes I mean, again we assume for the variable, we assume the continuous variable. Where this for the SEM to analyze the to estimate the model. So here, as I lectured today, we assume X continuous, Y continuous, right? But of course, sometimes ordinal variable, categorical variable, it cannot be continuous. Categorical means that your education level, bachelor, master, PhD, or lower than bachelor. Each category is not connected to each other. It's not 1, 2, 3, 4, right? So in this case, we can call it we can call it category variable. Ordinal variable, I also lecture last week. The order, the ranking, which method you prefer, how much you intention to use. I mean, okay, so Hong Kong government now want to introduce the autonomous vehicle. And then what is your intention? 1 is the very strongly want to use. 2 is the strongly want to use. 3 is the neutral. 4 is the strongly not want to use. 5 is strongly not want to use. This is the ordinal. Okay? So here, in this case, Likert scale, binary items, count data. So it's violated continuous assumption. So in this case, also the unbiased. If you estimate the SEM model, the result can be unbiased. Unbiased means the beta. Okay? And then in this case, of course, I mean, we also have some solution for the advanced estimator. So I mean, just for your knowledge, weighted least square, some is WLSMW, something blah blah blah, and then CVM, continuous categorical variable methodology, something blah blah blah. But what is the most general one? Weighted least square. So this is the one you can imagine. If this is the advanced of the OLS, right? Ordinary least square. This is the weighted least square. So, but I mean the detail. I mean it's okay. So others are okay. I mean nonlinear, linearity. So I mean this is the summary. So normally you can use the SEM model in any data, but since of the MLE limitation in MLE estimator, so there are some identification issue. In this case, what you need to do, I mean, some advanced estimator. I mean, not detail about this estimator, but I want to teach you in this class is that there are some advanced estimator rather than MLE, maximum likelihood estimator, rather than maximum likelihood estimator. There are some more advanced one. So if your PhD work is suffer with this issue, then you can study more detail about this, more detail by yourself. Okay. So, I mean, the detail of this algorithm for each, I mean, is very difficult. I mean, so it's not easy within this class. Okay. So, any questions so far? So, because last week I feel many students, the contents was last lecture was too difficult. So today I make it a little bit easier. So is it better this week or is it better last week? This week is better. Okay, I see. Okay, I see. Okay, then let's finish this class today. And then other thing is okay, but one thing, assignment 1. Okay, remember. Okay, so see you next week.